Hello student, in this video we are going to learn one of the important concept in structural analysis, that is analysis of redundant pin jointed frame. Pin jointed plane frame already we had discussed in the previous video, the concept of frame and the concept of indeterminacy of the frame. So the frame which we analyze in two dimension and every joint of the frame is pin or hinge, that frame we call as a pin jointed plane frame. Now when you check the statically determinacy of the frame, then we have the frame is statically determinate or statically indeterminate. So statically determinate truss or statically indeterminate truss. Now to find out the degree of indeterminacy of the truss, it will be summation of degree of external indeterminacy plus degree of internal indeterminacy. So externally indeterminacy or determinacy is related to the support condition of the structure and internally is related to the member forces. So same we can apply for statically indeterminate truss also. You can find out it externally as well as internally. So when you check the truss for statically determinacy, then it will be for external, then we should have this condition in the truss that number of unknown reaction is equal to number of available static equilibrium equation. Then the truss become externally determinate truss. Otherwise, if this condition is not satisfying the structure, if number of unknown reaction is more than number of available static equilibrium equation, then your truss becomes externally indeterminate truss. Now second is when you have to find out the statically determinacy of the structure internally also. So internally when you check the statically determinate truss, then we have the condition m is equal to 2j minus 3, that is m is the member forces, number of member forces, j is the number of joint, and if this condition is satisfied by the truss, then the truss is statically internally determinate truss or stable truss. So if this condition satisfied, then we can call it's a determinate truss internally. And if the structure is not satisfied this condition, m is not equal to 2j minus 3, then the structure or truss becomes statically internally indeterminate truss or understable truss. Now to analyze the statically internally indeterminate or unstable truss, we again divide this truss into two conditions. That is, the first one is when m is less than 2j minus 3. Means in the truss when member forces is less than 2j minus 3, then that truss becomes statically internally indeterminate, or we call it understable truss, or we can say deficient truss. Deficient truss means there is a deficiency of the member in the truss, that is m is less than 2j minus 3. And another condition we have is m is greater than 2j minus 3, means where member forces is more than 2j minus 3 condition, then that truss we called statically internally indeterminate truss, or we also call it overstable truss or redundant truss. So there is a redundancy of the member in the truss, or there are some member forces are more than required in this case. So let us discuss with the one example of truss. So here is one example of deficient truss ABCD, and here is one more example of truss which is a redundant truss. So ABCD which have two members additional compared to this previous one. So let us check the stability of this truss internally. So in the first condition, in the first truss we have 4 member. So m is 4, number of joints are 4. So j is 4. So by putting this 4 is less than 5. So here there is a deficiency of one member to make this truss stable. And in the compared to this first one, if you check the number of members in this truss, the number of members in the truss are 6 and number of joints are 4. So 6 is greater than 5. So if you put in this condition m is greater than 2j minus 3, then we got 6 is greater than 5, means there is a redundancy of one member in the truss. Means if you remove one of the member from the truss, then this truss becomes a stable truss or determinate truss. So particularly in this video we are going to learn how to analyze redundant truss or redundant frame. So let us discuss analysis of redundant trusses. So figure first shows the redundant frame carrying an external load W. So here that frame is that redundant truss. So which is supported on hinge support at B and roller support at C and subjected to the point load W1 at A. So if you see the determinacy of this truss is determinate externally, because we have number of unknowns in this truss are 3, means 2 at this hinge support and 1 is at roller support. So number of unknowns at 3 and number of available equations also we have 3. So this truss is statically determinate externally. But if you find out its internally indeterminacy, then it will be equal to m is equal to 2j minus 3. So if you check its indeterminacy, this truss is redundant truss. Okay, so here there is a one more member, or a member of truss is more than required. So this truss is statically internally indeterminate, but it is externally determinate, but internally it is indeterminate. So we have to analyze now this truss for the analysis of redundant member. So figure shows the redundant frame carrying an external load, and let S1, S2, S3 be the forces in the various member of the structure. So here S1, S2, S3, S4 and S5 are the forces in the truss because of this applied load W, and tension in the member BC, Bx, means we call this BC is a redundant member in the truss, means extra member not required for the stability. So we consider here BC is a redundant member and the force in the member BC is X, which is unknown here. Okay. So we have to find out that unknown redundant force member. Now if now a member BC is be removed, but the effect are retained by applying the pair of forces X at B and C, and the forces in the member of the structure remain unaffected, and which is shown in the figure number 2. So we replace now this BC member by the pair of forces X. Okay, because of this replacement, there is no effect on the member forces. The member forces remain S1, S2, S3 and S4 and S5, and there is a force X we applied at B and C alone. So here structure become determinate, but there is one unknown force is there, X. We cannot find out that X by statically determinate condition or statical equilibrium equations. So the effect is unchanged, but because of applying of X pair. The next is figure 3rd shows the frame without a member BC, and for the given load W applied on the structure, let P1, P2, P3, P4 and P5 are the forces in the member of the structure. So in the analysis, the next step is that we have to remove totally the redundant member from the truss. So here you can see the figure where BC member is totally removed from the structure, which is redundant. Now if you check the stability of this truss is stable now, or we can say determinate truss because of removing this member. Now because of this applied load W1, we can find out the forces in all the members, and which we call it here P forces. Okay, so in the analysis, the first step is that without removing the redundant member, you have to find out the P forces in the structure because of the applied load. Now figure 4 shows the same frame but subjected to a pair of forces X alone at B and C. So the next step is that we have to remove the external load and we have to apply the pair of forces X at B and C alone. And because of this application of forces, whatever the forces develop in the member of the truss, that we call as P1 dash, P2 dash, P3 dash, P4 dash and P5 dash. So these are the forces in the member due to this system. So when you have to find out the final force in the members, because of when you analyze the redundant truss, then we have that final force in the member is addition of P1 plus P2, means P1 is the force in the structure because of only external loads, and P1 dash is the force because of the redundant force, or we can say pair of forces X. So we have to find out final force is the addition of P1 plus P1 dash. Similarly, S2 is equal to P2 plus P2 dash, S3 is equal to P3 plus P3 dash, and so on. Now figure 6 shows the same frame subject to the pair of unit forces applied at B and C. Let K1, K2, K3, K4 and K5 be the forces in the member of the structure due to the pair of unit forces. So here what you have to do, you have to apply the unit forces. You have to take x common, means by replacing this x or by taking this x outside, we just take one unit forces we applied at B and C. So we will find out the effect of these unit forces in the member of truss, and that effect is we called it K1, K2, K3, K4 and K5. Means we are finding out the effect of these unit forces on the member, and then we multiply that effect with x unknown force, that is this x. So we got the force in the member because of this application of x forces at the B and C. So K1, K2, K3, K4 be the forces in the member of the structure due to the pair of unit forces. So when you have to find out P1 dash, the P1 dash is the force in the member because of the application of pair of forces X at B and C. So if you have to find out the P1 dash, it will be equal to each member force because of unit force applied at, in the place of redundant, multiply by x. So if you have to find a P1 dash, it will be equal to x into K1, then P2 dash is equal to x into K2, P3 dash is equal to x into K3 and so on. So if again you have to find out the final force S1 in the structure, in the redundant structure or redundant truss, then S1 is equal to P1 plus P1 dash, but we have P1 dash is equal to x into K1. So by replacing P1 dash is equal to x into K1, we have S1 is equal to P1 plus x K1, S2 is equal to P2 plus x K2, and S3 is equal to P3 plus x K3 and so on. So we have total strain energy stored by this frame. So generally the pin jointed plane frame are the axially loaded frames. So in the strain energy in case of axially loaded structures are W is equal to P1 square P square L upon 2AE. But we have to find out it for total strain energy by the frame. So we have to take summation. So W1 is equal to summation of, so instead of P1 we have a total force S1. So W1 is equal to summation of S1 square into L1 divided by 2A1 AE. So this is the total strain energy stored by the axially loaded frame. So where L1, L2, L3 are the lengths of various members and A1, A2, A3 are the cross-sectional area of the various members, and E is the Young's modulus. So by replacing the total force is equal to summation of P1 plus Kx1 square. So if you have to find out the any member, any force in any member of the truss, final force in any member of the truss, then it will be equal to P1 plus Kx1, so whole square into L1 upon 2A1E. But we have, according to Castiglione's second theorem, the partial derivative of total strain energy stored into the structure with respect to redundant force will give the zero displacement. So by this condition, if you take the differentiation of the strain energy with the redundant force delta x, that is delta W1 is equal divided by delta x is equal to 0, is nothing but the Castiglione's second theorem. And according to that, by putting the value of W1 in this equation, we have delta is equal to summation P1 plus Kx1 square into L1 upon 2A1E divided by delta x is equal to 0. So by taking differentiation of this term, we'll take we apply U into V rule. So we'll take first differentiation of this P1 plus Kx1 square, because L1 upon 2A1E is a constant term. So this term is as it is. So L1 upon 2A1E as it is, by differentiation of this whole term, as we are taking x square, so x square differentiation will be 2x square, so 2x, so it will be 2 into P1 plus Kx1, but P1 is again constant, and the differentiation of K with Kx1 with respect to delta x is equal to K or K1. So we'll take here K1 outside, so K1 into L1 divided by 2A1E is equal to 0. So this is the differentiation of this delta 1 with respect to W1 with respect to redundant force. So by taking by these two get cancelled, and by multiplying with the inside the bracket, we got here the term summation P1 K1 L1 divided by A1E plus x summation K1 square L1 upon A1 into E is equal to 0. So to find out this x, which is nothing but the redundant force, we have minus summation P1 K1 L1 upon A1E divided by the summation K1 square L1 upon A1E, which is nothing but the redundant force in the structure. So if the cross-sectional area and Young's modulus be the same for all, then we have the equation of x is equal to minus summation P1 K1 L1 divided by summation K1 square L1. So there are following steps may be followed in the analysis of redundant frame. The first is that we have to find out the degree of indeterminacy of the truss. Then after finding out the indeterminacy, we have to select the redundant member in the truss structure. Now to analyze this redundant member or to analyze the redundant truss, we have to remove the first redundant member in the truss structure and find out the P forces in the member of the truss for the given external load system. Then remove the given load system and apply the unit load pair assuming either compressive or tensile in place of redundant. Then find the K forces in the member of the truss. After that, find out PKL by AE term for every member of the truss and K square L upon AE for each member of the truss. And after that, find out the summation PKL by AE and summation K square L upon AE for each member, or after finding out each member, find out the summation and find the redundant force X is equal to minus summation PKL upon AE divided by summation K square L upon AE. And after that, find the force in any member of the truss by the relation S is equal to P plus Kx. So this is the general procedure you have to follow for finding out the member forces in the redundant structure. So let us discuss one numerical of analysis of redundant truss. So analyze the frame shown in figure for the forces in the various member. All the members may be assumed to have same L upon AE value. So this is ABCD truss and subjected to the external load 5 kilonewton at point B. So first we have to check that the stability of this truss by the first step. So degree of indeterminacy of the truss. So first is degree of external redundancy. So degree of external redundancy is equal to R minus E. So R minus E means number of unknown reaction in the structure minus number of available equations. So number of unknown reaction in the structures are 3. So 2 at this hinge joint and 1 at this roller. So total is 3 unknown reactions are there. So 3 minus 3, 0. So this truss is statically determinate externally, but to find out its degree of internal redundancy, we have the equation m minus 2j minus 3. So member of the truss are 6 and the number of joints in the truss are 4. So 6 minus 2 into 4 minus 3. So degree of internal redundancy we got here 1. So to become this truss stable, or we can say determinate, there is a one extra member is there to make this truss. One extra member we have to remove from the truss structure to make this truss a stable truss. So total degree of redundancy is 1. So let us identify one of the member in the truss as a redundant and remove that member for the analysis. So select the redundant member is the second step. So let us select here AD member is the redundant member. So when you remove this AD member from the truss structure, then the structure internally determinate truss, internally determinate. Now third step is remove the redundant member and find out the P forces in the member of the truss for the given load system. So here you can see here the AD member is removed from the truss and we can find out the first external reaction. So here RC reaction we got here 0 and RD is 5. It's very simple. By condition of equilibrium applying for whole truss, we can find out this external reaction RC 0 and RD is 5 kilonewton. So by considering a joint analysis, we can find out all the member forces. So first we consider joint A. So when you observe at joint A, there is no external load at joint A. So both the forces which is available at joint A, that is PAB and PAC become 0. After that we can consider again joint C. So at joint C, if you observe again, the reaction is 0. So both the forces, member forces become also 0, that is PCB and PCD is also 0. Now we'll take the last joint, which is joint D, and we'll draw the free body diagram of joint D separately. So this is the free body diagram of joint D. The RD reaction is there, which is 5 kilonewton. The member force PBD that we have to find out, which is acting in the downward direction. We assume it is compression in nature, and PCD is already 0, so it is 0 force shown in the FBD. So when you apply the condition of equilibrium, summation of phi is equal to 0, then 5 kilonewton is acting in the upward direction, so plus phi u minus PBD is equal to 0. So PBD is equal to 5 kilonewton. So the nature of PBD we got here compression, because we assume it compression and we got the positive sign, so nature is correct. So PBD is 5 kilonewton compression. Now remove the external load and apply the pair of unit load in place of redundant and find out all the K forces in the member. So here we have removed the AD member from the truss, and now we apply the pair of unit forces at A and D. You can assume it tensile or you can assume also compression. Here I assume it a tensile in nature, compression in nature. So consider joint A in equilibrium now. First joint A we'll consider for the analysis, and we'll draw the free body diagram of joint A. So the forces acting at joint A is KAB force, then KAC force, and this unit force applied at A, which is acting at an angle of 45 degree. So now applying the condition of equilibrium for the joint, we have summation effect 0. So KAB is positive, minus 1 into cos 45 is equal to 0. So you got the value of KAB is equal to 0.71, and which is a positive again. So the nature we assume for KAB is correct. We assume it tensile in nature and we got the positive sign. Now next is summation Fy is equal to 0. So minus KAC minus 1 sin 45 is equal to 0. So KAC is equal to, plus 1 sin 45 is equal to 0. So KAC is equal to sin 45. So KAC is equal to 0.71. So now to find out the member forces at joint C, consider the joint C in the equilibriums, and drawing the free body diagram at joint C, we have KCD member force, then KCB, and the KAC already we have found out, which is 0.71. So by applying the condition of equilibrium at joint C, we have summation of Fy is equal to 0. So summation of Fy is equal to 0 when you apply it for this joint C, then it will be equal to 0.71 is positive, minus KCB sin 45 is equal to 0. So KCB is equal to 0.71 upon sin 45, which is equal to positive. And so the nature of KCB we assume it correct. We assume it compression in nature and we got the positive sign. So KCB is compression. Then summation Fx is equal to 0. So KCD we got summation Fx is equal to 0. Then it will equal to KCD is positive minus KCB cos 45 is equal to 0. So KCB is 1. So KCD becomes cos 45 is equal to 0.71. Again we got a positive sign here. So the nature we assume for KCD is correct. So it is tensile in nature, and due to the symmetry of the truss, KDB is also a same, which is equal to 0.71, and which is the same nature of that member force, which is tensile in nature. So this is all about the K forces developed in the truss because of the application of unit forces at in the place of redundant. Now to find out the effect of all the members and to find out the redundant force, we have to find out the PKL by AE, K square L upon AE, and summation PKL upon AE and summation K square L in AE for every member, and after that we have to take summation. So for this purpose, in the analysis steps, you have to do this, you have to make this table like this. So the table consists the name of member, then magnitude of P forces, magnitude of K forces, then PK term, K square term, and then the final forces. So here the members are AB, AC, AD, BD, BC and CD. All the remaining forces are 0, only BD is present, which is 5 kilonewton. And also I listed all the K forces we have calculated in the last slide. And the next column is pkl upon ae, but here your truss is of same length, cross sectional area is also same, and the modulus of elasticity is also same. So we just take a pk term here. But if you are having truss whose length is different, whose members lengths are different, area is different, or if modulus of elasticity is different, then you have to again take one column for length, one column for area, and one column for modulus of elasticity. But if your lengths and areas and cross sectional area, you can directly find out the product pk only. Then after that again k square we can take only taking the square root, squaring on k forces, and pk is a product of p into k forces. Now to find out the final forces in the member of the truss, we have formula F is equal to P plus KR. Now already we know P and K, but R is remain to find out. So R we got when you get a summation term. So let us find out the summation PKL upon AE. Again L upon A is constant sum, so we can just find out summation PK by just taking the summation of this column, which is equal to minus 3.55, and summation K square is equal to 4.016. Now let us find out the redundant force, which is the last step of this analysis. So R is equal to summation PKL upon AE divided by summation K square upon AE. So summation AE is constant, so R is equal to minus summation PK upon K square. We got here 0.88, which is minus. So we got the final formula or final forces by multiplying the K forces with this X redundant force. So we got final all the forces in the member by given by F is equal to P plus KR. So we multiply this redundant force to the K forces. This is the redundant force correcting factor we got here. When you multiply here all the K forces which we gave for only unit forces, then we'll get the effect of redundancy here, and plus all the P forces for the external applied load. Then when you take the summation of this whole effect, then we'll get the final force in the member of the redundant truss. So like this we can analyze the analysis of redundant trusses. Thank you.